For this lab, there was a lot of setup, and it took a long time, so I'm going to walk you through as much as I can. So we started with aligning the laser. As usual, we did it with a pinhole starting up close to adjust the position, and then far away the tip tilt to align it to the rail. The next thing we put in was this mirror, and we have it on a rotation stage and one translation stage. Ideally we'd have two, but we were limited on resources. We have it on all of this because later in the lab we're going to look at off-axis, and this allows us to look off-axis into the system. So then the next thing we put in was the microscope. So similar to last week, we made sure the numerical aperture we used, 0.25, was large enough, larger than the numerical aperture of the lens that we use, which was 0.125. We have the microscope on translation stages so that we can focus on different locations as we look at different holes in the Hartman test and off-axis. And then, so after that, we put in the spatial filter, again on translation stages and for alignment. And we have an objective and a collimator for the beam expander to make the beam wide enough to cover the complete Hartman mask. We put a pinhole in here to stop down the rings that occurred from our spatial filter. And then we have the lens with the Hartman mask. This one has 5 spots on it, 1 in the middle, 2 on each side, left and right, and 2 top and bottom. This is to help us look at the coma and astigmatism present in the system. And we used a pinhole, and then sometimes we used some paper to isolate the different dots or series of dots to look at the aberrations in the lens.
It basically demonstrates what a Hartman mask does. It has the 4 holes at A, B, C, and D, and the top and bottom hole should map to the same point, and the left and right hole should also map to the same point here. The inner circle represents either a smaller field angle or when the light has been stopped down, which demonstrates that light closer to the axis has less coma. So for the portion of the lab where we were measuring coma, we first had everything aligned along this rail with the laser going through the center hole just to get our reference position. We then shifted the microscope 5 millimeters this direction and adjusted the mirror so that the light was going through to effectively create a field angle because coma is not noticeable on axis. We then used the stop without the white things, that was for the astigmatism portion, to direct where the light went through, or which hole the light would go through on the Hartman mask. And so we took a measurement with the light just going through the left hole, just going through the right hole, just going through the top hole, just going through the bottom hole, adjusting the microscope to line these spots with the crosshairs of the microscope in order to record those positions, which we would then use to find the coma.
This picture illustrates how astigmatism causes both a tangential and sagittal focus, which we can use to find the astigmatic error in the system.
In the next part of the lab, we were measuring astigmatism, and so to do that, we found both the tangential and sagittal focus of the lens. So to find tangential, we used this device to block off the side holes of the Hartman and only got light through the top, middle, and bottom, and then we adjusted the microscope so that all 3 of these spots were co-aligned with the crosshairs, and then we switched this so that the sagittal focus could be found. So that's just the horizontal dots, and then we adjusted the Z position of the microscope so that those 3 dots were aligned, and the change in distance was related to our error in astigmatism.
So we modeled our lens in ZMAX. You can see here the plano-convex lens we had. We faced it that way because the shape factor affects coma as well as spherical aberration. If you look at this, the aberration coefficients, you can see that spherical aberration is dominant by far, which is to be expected as we saw in the previous lab, but there's also coma and astigmatism. The ray fan plots demonstrate what I just discussed, that spherical aberration is the dominant aberration.
From the data we received from this lab, we used these 3 equations to determine the tangential coma from the error in Y, the sagittal coma from the error in X, and the astigmatism from the difference between our measured tangential and sagittal coma. At our plus 5 millimeters field, or our full field, we had these values for our changes for our coma, and so we got about these values for our coma, and this one for our astigmatism. So these are rather large, and theoretically your sagittal coma should be 1/3 of your tangential coma, which we did not get here. This is actually, and so we see that our errors were not exactly accurate, although we believe our astigmatism was fairly accurate. And if we moved also to a 3.5 millimeter field, and these were our numbers, so these were a little more accurate, we think, because our values for W of coma were very similar between our tangential and sagittal coma, and our astigmatism was relatively similar to our astigmatism from before.